Okay, in this video part, we're going to talk about how we apply Gauss's law practically, which the answer to that question, long story short, is there are not lots of ways to apply Gauss's law in this particular form. All right, so let me just summarize Gauss's law again for you. This is Gauss's law in a nutshell, which is if you add up lots of information about the electric field around the outside of an object, it tells you something about the total charges that are inside the object. But it doesn't tell you much about where exactly those charges are distributed. So in that sense, it's both helpful and it's also pretty useless. Because if you want to know are charges over on one side of this nutshell or on the other side, then you don't really have much value to Gauss's law. All right, and the way we described that mathematically was that the surface integral around the outside of this nutshell, if the nutshell is closed, of the electric flux density dotted with a small surface vector equals a integral of the charges that are inside. So just to illustrate this, right, a ds vector is a vector that points through the surface going out, right? So ds points outward. So it specifically captures outward flowing electric flux lines. Electric flux lines that go inward are going to have a negative contribution of d dot ds, whereas d dot ds, a positive contribution, is going to capture the outward flow, and rho v dot dv is going to capture little charges that are inside the nutshell. All right, so d dot ds is positive if flow is outward, and d dot ds is negative if flow is inward. And that makes sense. If we have positive charges, then electric flux lines are going to be swarming away from that point, and so that's going to cause an outward flux, therefore a positive charge on the inside. All right. Now, the way you actually would apply this in reality, right, the way you would use Gauss's law to sort of solve an electric field problem, I give you some configuration of either charges or fields, and I ask you to find the other one. The way you would actually apply it is, number one, you choose a coordinate system. All right. Step number two, for analytically solvable problems, you would pick a Gaussian surface. Which is some kind of surface that encloses the charges that you want to know something about. So pick the Gaussian surface, and you want to leverage symmetry somehow. So since we've got a triple integral on the right side of that Gauss's law and a double integral on the left, you want to pick something that has symmetry. So if you have a single charge in the middle, a sphere around it would be a nice Gaussian surface, because now everything is kind of the same as a function of angle around the sphere. And so it collapses your three-dimensional integral or your two-dimensional integral into just one dimension and makes it actually solvable analytically. Number three is you substitute your differential volume and your differential surface. By the way, step one includes picking the origin location. All right, step three is substitute dv and ds given your selection of your coordinate system. Step four is substitute for rho v into Gauss's law. And step five is to solve as much as you can. All right, so this is the answer. And if you open up any physics textbook, they'll probably walk you through these steps, and they'll have a couple of examples. As a simple example, if d is parallel to ds, then that implies that d dot ds equals just the magnitude of d times ds, right? So that's one way you can leverage symmetry. If you ensure that your electric flux density is always parallel to your surface vector, then you can take that complicated dot product and just reduce it to multiplying two numbers together. Right, so that's one of the tricks that you'll find. Now there's an example in the notes that kind of walks you through these steps so you can see how one might do it. It's stuff you may have seen in earlier physics classes, and it's a charged sphere that has radius d, and it's a charged sphere for which the charge density by volume is some constant times r squared. Right, so you basically got no charge in the middle, and as you go out toward the outer parts of the sphere, you get increasingly dense charge. And the answer to the question is, what is the electric field that results from this configuration, both inside as well as outside the sphere? There's an example in the notes, and so you're welcome to take a look at that. The truth is, though, that in reality, Gauss's law in this integral form is pretty useless, right? So I'm introducing it here so you can understand the concept of what Gauss's law means, how it relates sources to electric flux line. The truth is that there are a very small number of scenarios for which you can actually solve Gauss's law in an integral form. Something where you've got a very nice, clean, even symmetry that enables you to reduce these double or triple integrals down to easy analytical solutions. And again, pretty much every example of this you can find in a few different standard textbooks. In reality, no problem has this perfect symmetry. And so you cannot, in general, evaluate these integrals and therefore learn from them. The best you can do is maybe do it numerically, where you split up space into small little, cubic pieces, and then you can solve it like that. But that's also pretty unhelpful. So while I'm introducing Gauss's law, it is not my expectation in this class that you understand how to perform these double and triple integrals and how to set up the integral. That's probably useful in physics classes, but in real life, it's not useful at all. And so the next form of Gauss's law that we're going to cover in the next lecture is going to be much more useful, and where we're going to take this integral form and reduce it into basically very small pieces and talk about how Gauss's law applies on a micro scale. And that will be the next lecture video, and that's going to be much more useful, even though it's still not something you can usually do analytically.